Hello everyone, this is Stephen Ramsden, the founder and director of the Charlie Bates Solar Astronomy Project. I am located in Atlanta, Georgia, which is in the southeastern United States. We are at 34 degrees north latitude and about 83 degrees west longitude. It's my pleasure to be with your classroom and try to share some solar astronomy with you. It's a hobby that we love. And we love to share it with other people. We believe that this is a fantastic way to learn about the solar system and to encourage you to get more involved in space travel and science in general to make a better world. So we'll take off the American flags here in a minute, but go USA is what I say. And my friend Rob Black is in Australia. He is the director of our Australian chapter, which is in a region called the Burdekin, which is north of Brisbane, Australia, near Townsville. So he's providing us with a live view of the sun that you'll see in a few minutes when I turn it over to Rob. And we also have our Kosovo director of the Charlie Bates Solar Astronomy Project, Pranvera Hasini, who is on the broadcast with us. We're expecting our Costa Rican director, Marcy Malavasi, and possibly her daughter Abby to be on the show also with us. Our intention with this is to teach you about solar astronomy and get you interested in the sun. So how many of you already know something about the sun? Can anyone shout out and tell me what the sun is made of? What is the sun made of? If you're saying gas or lava or rocks, those are all popular things that people say in response to that question. The sun is not made of rocks. The sun is not made of lava. The sun is, it's interesting how so many people know nothing about the sun. The sun is the most important thing in the universe to your survival. It provides us with energy. Every living thing on this planet derives its existence from the sun. Without the sun, we would not be here. The planet would not be here. Your dog would not be here. The cows, the horses, the birds, nothing would be alive. We would not be alive. So the sun is by far the most important thing in the universe to our existence. But if I ask that question, what is the sun made of? If I ask that question to hundreds of people in my own country of the United States, I'll probably not get anyone to give me the correct answer. So we're going to start out with this. The sun and every star in the universe is made out of hydrogen. Hydrogen is the most common element in the universe. 75% of our sun is hydrogen plasma. Hydrogen plasma is hydrogen in the fourth state of matter. You have solid, liquid, gas, and plasma. So plasma is the fourth state of matter. The sun is composed of hydrogen, gas, and plasma. And what happens in the sun to make it hot? Why is the sun hot and bright? If I ask that question, I'll get a bunch of wrong answers too. Almost no one knows that either for some reason. I want you to know that before we're done with our lesson today. The sun and every star in our universe works with exactly the same principles of physics. And we'll talk about those now. The sun is a giant ball of hydrogen plasma. The force of gravity, you know, the same force that causes my hand to drop to the earth, gravity, causes our sun to try and collapse towards its center because the gravity is the strongest at the center. All the gas wants to get to the middle of the sun. And when this happens, a great deal of pressure is put on the core of the sun. You have to remember the sun is 875,000 miles across. It's very, very large, over 1 million kilometers across. All that gas pressing in on the core of the sun causes the atoms to move very rapidly in the core. The hydrogen is moving very quickly, so fast, in fact, that it smashes together in a process called nuclear fusion. And when this process happens, on a very basic level, hydrogen atoms fuse together and they form the second most common element in the universe, which makes you talk funny if you breathe it in from a balloon. Does anybody know the name of that element? Helium. That is right. Helium is created in the process of nuclear fusion in the core of the sun. Helium is the second most common element in the universe and also in our sun. Helium makes up about 24% of our star. So it's 75% hydrogen. It's fusing together, turning that hydrogen into helium in the core of the sun. And so far, we've manufactured about 24% of the sun's mass is helium. So we're about halfway through the sun's life. And when it runs out of hydrogen, when it's all been fused into helium, a lot of strange things will happen to the sun. It will explode into a red giant, and then it will collapse back down until it gets hot enough to fuse the helium atoms. Then they'll fuse into carbon, nitrogen, and oxygen. That's a long way off. That's 5 billion years away. So we don't have to worry about that right now. But again, the process that causes the sun to produce heat and energy is called nuclear fusion. It only happens in the core of the sun, which is about 10% of the sun's actual mass. And the process combines hydrogen atoms together to make helium atoms. Now, when that is done, a certain portion of the hydrogen is released as energy. And there's an equation that an old German guy wrote back in 1905 that tells you exactly how much energy is created in that process. Does anyone know that equation? I can't hear you. The equation that tells you how much energy is created in nuclear fusion? I bet a lot of you do. The equation is E equals mc squared, and it was part of the special theory of relativity, which was put forward by Albert Einstein in 1905. The E in that equation stands for energy, the M stands for mass, and the C stands for the speed of light. It's just a constant that makes the equation work. Energy equals mass times the square of the speed of light. So you get a great deal of energy from a very, very small amount of mass. If I were to take my pinky, just a tip of my pinky right here, and convert it directly into energy, there would be enough energy in just that much pinky to destroy the entire state of Georgia, where I live in the United States. There's a great deal of energy in a very small amount of mass. So E equals mc squared is the equation that tells you how much energy is produced in nuclear fusion. So let's move on. This energy is produced in the core of the sun. It slowly radiates outward from the core into the outer layers of the sun. You have the convective zone, which is right after the core, and it is exactly what it means. Convection means heat is moving around through the zone. So the core produces the energy. It's very hot, about 26 million degrees Celsius. As it flows through the convective region, it cools down drastically, produces magnetic currents in this region. It cools down drastically till it gets out to the photosphere of the sun. And the photosphere is what you see in a normal white light solar telescope. We're not using that today. We're using a special telescope that I'll talk about in a minute. But the photosphere of the sun is generally what people refer to as the surface. And on the photosphere of the sun, you can see sunspots. It's mostly white with black spots. And that is the point where the sun's radiated energy becomes transparent to visible light. And we call it the surface of the sun, but there's really no surface of the sun. It's just a large core of nuclear fusion with energy radiating out from the center, getting to the photosphere. At that point, some things happen. After the photosphere, the energy continues to radiate outwards, but it's now mostly transparent to visible light. That region is called the chromosphere, and that's what we're looking at in the special telescopes that Rob Black has online in Australia. So the chromosphere is still about 74% hydrogen and about 25% helium, and there's 1% trace elements. What's a trace element? Well, everything else on the periodic table basically is present in the chromosphere of the sun, and it accounts for about 1% of the sun's mass. So you have hydrogen, carbon, nitrogen, sulfur, iron, phosphate, uranium. Every element on the periodic table that naturally occurs on our planet is present in the sun's chromosphere. One of these elements, hydrogen, does a very special thing that allows us to observe the sun. The hydrogen atoms in the sun's chromosphere absorb the light that's being ejected from the photosphere. When the hydrogen atom absorbs the light, it likes it. It says, hey, here's some light. I like it. So the hydrogen atom absorbs the light, and it causes a black line seen in the spectrum of the sun. You've seen a rainbow before. A rainbow is just the sun's spectrum. All those colors, all the way across the rainbow, come out of the sun all the time. When that light hits the hydrogen atoms in the sun's chromosphere, the hydrogen absorbs one portion of that visible light spectrum, and it creates a black line right about there in the hydrogen alpha region of the spectrum. It's very important that you understand that. The absorption line created right there in the visible light spectrum in the red region is proof positive that there's hydrogen in the sun's chromosphere. And that's the case for any star. Wherever you see that one little line in the red area, that means there's hydrogen present in whatever you're looking at. That's how we identify what stars are made of. All the different lines throughout the spectrum tell us what the star is made of. So this hydrogen alpha absorption line created by the hydrogen atom in the sun's chromosphere is caused because as soon as the hydrogen atom absorbs the light, it immediately re-emits the light. So it absorbs it, makes the black line right here, re-emits it. And when it re-emits the light, it re-emits it at the same wavelength that it absorbed it, which is 656.28 nanometers, or that's called the hydrogen alpha absorption line. When it re-emits that light, it's called the hydrogen alpha emission line. Now, Lunt Solar Systems provides us with special telescopes that are designed to specifically see, just one moment, my dogs are very excited about the sun too. So that's Charlie, my dog. Lunt Solar Systems provides us with telescopes that see this hydrogen alpha re-emission line. And the way they see it is they're special telescopes, and when you look through it, instead of seeing full color, all the wavelengths of light, what you see is just that one re-emission line from hydrogen right there. And the telescope blocks everything else coming out of the sun. So you only see the hydrogen alpha emission line. And what you see in that telescope is exactly what Rob Black is showing us from Australia. And I'll turn it over to Rob for a minute, and he can tell you what he's doing and where he is, and a little bit about himself. And then I'll take back over and explain to you what you're seeing in his telescope. So is everybody ready to listen to Rob Black from Australia? Very good. Take it away, Rob Black.
Good day, everyone. How are we all? Glad to make your acquaintance today. And just to give everyone a little bit of information where I am, I'm in a place called Home Hill, which is in a place called the Burdekin. And if anybody wants to look at an atlas, the map of Australia, we're about an hour south from a place called Townsville in North Queensland. And I'm set up out in my backyard at the present moment, and I am showing you the sun in what we call hydrogen alpha from one of my Lunt LS100 telescopes. And it is being broadcast to you all the way from Home Hill in Australia. But just a little bit about me. Like Stephen already mentioned, I'm the Australian director of the Charlie Bates Solar Astronomy Project, and I've been doing this now for about a year with all the equipment that I've got at the moment. I've got a Lunt LS100 double stack, which shows what you're seeing now, the sun and hydrogen alpha. I've also got a what we call a calcium K telescope, which will show the sun in calcium or very near UV, ultraviolet, and of course a Lunt LE100 white light, which shows visible light. So you can see the photosphere of the sun and also sunspots. One of my other telescopes I've got is the only one in Australia, which is a Lunt LS152. And that is a spectacular telescope, but I just thought I'd set up the three smaller ones to make it easier to broadcast to you guys. So, yes, it's amazing, isn't it? Yeah, it's the sun. It's one sun, everybody's sun. Nobody claims ownership to the sun, but here it is being broadcast to you from Australia. Stunning image, isn't it?
It certainly is, Rob Black. Thank you so much for setting up your telescopes. We're going to talk a little bit about what Rob's looking at and perhaps change over to the calcium scope shortly. But for now, we're going to talk about this image and what you're seeing. This is not fake. This is not the internet. This is not, oh, if you're wondering what I'm wearing, these are solar viewing glasses. And the Charlie Bates Solar Astronomy Project can send these to your school if you make the request through our Facebook page or solarastronomy.org. We're happy to send you out some glasses for your students. Just let us know. Totally free of charge, like everything we do in the Charlie Bates Solar Astronomy Project. But these special glasses allow me to look directly at the sun. See how dark they are? And they're free to you and your students if you would like them. Now, what we're looking at with this telescope, if you'll notice in the upper, let me get my glasses on so I can see better. There we go. Okay, so we'll split the sun into 4 quarters. You have your upper left, right, bottom left. We'll talk about the bottom left region on today's sun. First thing, notice that the image is going in and out of focus. That's perfectly normal, and that indicates humidity in the air. Whenever you look at a telescope, or through a telescope at night or day, what you see is you're looking through air. You're looking through water vapor and air that's above you. So that water vapor and different pressure air as it passes by overhead causes the image to go in and out of focus a little bit like this. These are exceptionally clear skies in northern Australia, some of the clearest in the world. So this is a very, very good image of the sun. You might notice some black lines in the bottom left quadrant. There's a dark spot almost in the middle of the sun there, and there's some black lines going away from that. There's also a couple of white lines that you can see. Now in the upper left quadrant, you see another couple of black spots with some white spots around them. And in the upper left, you see another black line. Okay? All of these different color variations indicate temperature of plasma. So if you see a white area, it's because it's hotter. If you see a dark area, it's because it's cooler. I say cooler, but none of this is below about 10,000 degrees Fahrenheit. The black areas that look like lines, those are actually called solar filaments, and they are clouds of hydrogen plasma that are being held aloft by magnetic field lines that come out of the sun. The entire sun is governed by magnetic fields. So just like the Earth's magnetic field is shaped like this, and it rotates with the Earth, the sun's magnetic field, since there's no solid core, no solid area on the sun, it's constantly twisted around and rotates in all kind of unusual ways. Okay? I think Rob is changing over to his calcium K-scope now, and that's fine. But those black areas and light and dark areas are caused by different color, different temperature gas on the sun's surface. Let's go back and look at that again. There he goes. The little tiny black spots. Yeah, Rob did look like he was pretty hot, didn't he? He was very sweaty because he's standing out in the sun providing you with free solar astronomy from Australia. I think that's pretty cool. He's about 20,000 kilometers away from me, and Pranvera is about 10,000 kilometers away from me. And we're all on this same broadcast just for your classroom. We want you to learn about science. So if you look around again, you'll see many different regions of different temperatures, and these are all caused by magnetic field lines that come out of the sun's core and go all the way out of the photosphere and into the chromosphere, which is what we're looking at now. Maybe I can get Rob Black to turn the gamma on his camera over to about 0.45 or 0.5, and that will show you some of the edge features on the sun. See how the sensitivity of the camera is being greatly increased now? And that's because Rob is turning the gamma control to a higher setting. Now notice on the left edge of your image, you see a little, what looks like a flame or a branch of a tree sticking out on the left. And over on the right side, you see a different shape, sort of clump on the right side, and there's another small prominence just above that. These are exactly the same things as these black lines in the middle. They're called solar filaments when you see them against the surface of the sun, and they're called solar prominences when you see them on the edge of the disk. And if anybody's wondering, this dark stuff outside of the sun, this is called space. This is where we live. You're on a little tiny rock orbiting around this giant ball of hydrogen plasma. It's absolutely amazing if you ask me. Now the solar prominences are sort of small today but they can get as large as the entire sun. So it's really an amazing view, and I want you to just take a look around and look at the different features that you can see on this. And I'm going to try to pull up a special photograph I took of the sun that shows you a little bit larger prominences, and we'll see how that looks. So here's an image. Let me screen share this for you. Just one moment. This that you're looking at from Rob Black, this is what we call raw data from the camera. And the way we take pictures of the sun like this, we take the raw data and we shoot about 1,000 frames of this video, and then we take the video and stack all the frames together into one image. And we take that one image, open it up in Photoshop, and tweak around a little bit with it, and you get this image. All right, notice what I was telling you. These bright areas are called active regions. These dark spots right here are called sunspots, like you might imagine. And these dark lines twisting around on the surface of the sun, those are called solar filaments. Anytime you have a group of things together on the sun, it's called an active region. So we have an active region right here that has filaments, sunspots, and some plage, which could be called plage or hot spots. These are crackling areas where there's solar flare activity. And I'm going to try to pull up a different shot here and show you another version of this if I can. Won't take long. Here's a real special one that you might enjoy. And if anybody can tell me what this image is showing, just one moment. What do you think this image is? Okay, notice the background is white on this image. That's just because of Photoshop. But there's a large black circle here. This is not a sunspot. Can anybody in the class guess what this is? That's right. This is the planet Venus crossing in front of the sun. This happened in 2012 on June 5th and 6th. All around the world you could see the Venus transit. And this is Venus transiting the surface. It started over here, and then it just slowly transited or orbited around the sun and was in a special position so that it was between us and the sun, and we could see the actual planet Venus right there. That's pretty amazing if you ask me. Let's see if we can get a little closer. Notice it's a little bit blurry around the edge of Venus. That's the atmosphere of the planet that you're seeing. So that's pretty fantastic if you ask me. And again, all these different temperatures of gas on the sun produce the dark and the bright lines. I'm going to show you one more image of what's called a solar flare. Solar flares are usually mislabeled by people, but this is an actual image of a solar flare here, taken by the same camera and telescope that Rob Black is using in Australia. And I want you to notice how, well, first off, how awesome this is. It's incredible. That is a really, really bright area of hot temperature gas right here. This is an X-class solar flare. Flares are rated by their strength, by their energy levels. X is the highest rating you can have in a solar flare. So this white area is 2 or 3 million degrees Celsius, while the surrounding area is around 10,000 degrees. So it's a gigantic collision of magnetic fields on the sun that cause these solar flares to occur. And these are monumental releases of energy. These solar flares can cause interference with radio transmissions on the Earth, problems with GPS satellite navigation. They can cause aurora in the north and south polar regions. And they are very, very energetic. They happen most of the time during solar maximum, but they can happen anytime, really. This image is still black and white, straight from the camera, without any Photoshop processing. So the black line right here, this is a very large, very long solar filament. Remember, it's a filament if it's on the surface of the sun, and a prominence if it's on the edge of the sun. They're both the same exact things, but for some reason scientists call them different things when they're on the surface and on the limb. Look here, here's one that's on the edge and also on the surface. Guess what that's called? You guessed it, a filaprom. solar philoprom. That's what they call this. So this solar flare was about an X4 solar flare. Lasted probably 15 minutes, blew a great deal of energy out into space towards the Earth, because remember, we're looking at this from the Earth, so this is the center and this is sort of aimed at us. And it threw that energy into the solar wind, which buffets our planet 24 hours a day with 300 to 600 kilometers per hour, kilometers per second solar wind. And this solar wind has been there since the formation of our planet. Our species has evolved with the solar wind buffeting our atmosphere. It's not going to kill us, but it does produce some strange effects in our atmosphere sometimes, especially when you inject a great deal of energy like from a solar flare into it. So we're going to go back and check with Rob Black and see if he's got something new for us and see what's going on there. Just one moment. Here I am in Atlanta. Remember, I'm probably 20,000 kilometers away from you. And we are going to go to Rob Black in Australia and see what he's got going on. Rob, do you have anything going on for us yet, or are you changing out your telescopes?
Okay, I was just going to say, Steve, just give me about 5 more minutes so I can change the camera out, and I'll show everybody calcium K.
Will do. And I'll take back over, and let me find a very awesome photo to show you on my Facebook. Just one moment, please. And you guys can think up a couple of questions you might want to ask your teacher, or email to us at solarastronomy.org. You can also get on our Facebook group for the Charlie Bates Solar Astronomy Project, and you can look at it there. So let's go here and see this fantastic resource that you and your teacher can use straight from the classroom via the internet. NASA has a website called Solar Dynamics Observatory. Okay? And I'm going to screen share this with you. Rob Black is currently focusing the calcium K image, but I'm going to screen share the NASA Solar Dynamics Observatory page with you. The address is sdo.gsfc for Goddard Space Flight Center .nasa.gov, or you can just search NASA SDO, and that stands for Solar Dynamics Observatory. And as soon as you get to that page, you see a live image of the sun in 2, 4, 6, 8, 10, 12, 14, 16, 18, 21 different wavelengths or readings from the sun. This is all live. This information is broadcast from the Solar Dynamics Observatory probe every 7 minutes. It's updated. And let's just click this one. This is extreme ultraviolet image of the sun in 304 angstroms, which is 30 nanometers, and that's extreme ultraviolet. So you can see it's very similar to what you looked at in Rob Black's telescope, except this is a totally different wavelength, and it's shot from outer space. You can show your students this any time of the day or night on the NASA SDO site. They also have, let me share this image with you so you'll see what I'm seeing. Just one moment. Okay. This is the NASA SDO site. I think Rob is presenting to everyone, so I can't make my screen bigger, but that's okay. This is the NASA SDO image of the sun live, and this is right now, and this is the same sun that Rob Black's looking at in his telescopes. Let me go over here and choose the wavelength that's going to correspond with the next image Rob is going to show you live from the sun, or at least the closest I can get to that wavelength. Let's look at this one, which is also an extreme ultraviolet, but this is pretty close to what you're going to see in Rob Black's telescope. This is 1700 angstroms, or 170 nanometers. It's still extreme ultraviolet, but what we're looking at here is sort of a photospheric, a chromospheric image, but a little bit higher in the chromosphere than the hydrogen alpha we were just looking at. And when we switch over to Rob's telescope, he's going to have it all set up and focused perfectly for us and tinted to the correct color for calcium K. There are calcium ions in the sun's chromosphere, And just like the hydrogen, these calcium ions absorb the energy at a certain wavelength, 304 nanometers, which is what we're going to look at in just a moment. And then they re-emit the wavelength at the same frequency. So what you see is a near ultraviolet image of the sun. Well, that's what we're going to see in Rob Black's telescopes here shortly. A near UV image. And as you can see, these black sunspots are scattered about the sun right now. This is exactly the same sun at the same time that we were just looking at in Rob's telescopes. But here's a sunspot here in a different wavelength. So it looks different in different wavelengths. That's my dog Charlie. She's very impressed with it too. Over here are some more sunspots, and over here is another sunspot. So you also notice a lot of bright areas. This is actually called plage, which is a French word that means beach. And these bright areas are just hot spots on the sun's chromosphere that are caused by the same electromagnetic fields that cause these sunspots. And if you look close on this one, there's a little bright spot next to that sunspot. And that's a crackling region that might become a solar flare if we're lucky. So this is what the sun looks like in a different wavelength. And it's the same sun at the same time. It's just a different wavelength. So let's go back and try out another wavelength on the NASA SDO site. Let's look at one that's really cool. Like this one. Hold on. All this high-tech stuff. There's a lot to operate. There you go. This is an image that puts together all the wavelengths that NASA SDO sees and combines them into one composite image. Look at all this extreme solar wind being ejected from the sun and all the different beautiful patterns in the sun's corona. And again, this is very, very good image that shows all the different wavelengths, all the different magnetic fields that are coming out of the sun and mixing together. Remember, the dark is cooler and the light is hotter. So you're seeing all sorts of hot and cold magnetic fields in the sun's chromosphere that are all interacting with each other and causing these beautiful displays. I mean, you couldn't paint this if you had to. This is Mother Nature at its best right here. Notice this dark region up here on the top. This is called a coronal hole. This is where the corona of the sun, or the chromosphere of the sun, is not quite as thick as it is in this region here. And this allows the solar wind to escape at a much faster velocity from the sun's chromosphere and photosphere. So whenever you have a coronal hole like this that's in the center of the sun, that means we're going to get a much faster solar wind, which will produce more bright auroras and have more of an effect on the Earth's atmosphere. Over here on the right, you have some very hot solar prominences or active regions that are producing more energy than the others. Notice how all these lines from this region go out and curve around and come back in. These are all magnetic field lines coming out of the sun that are manipulating the hydrogen plasma. So it's the same thing as if you were going to sprinkle some iron filings next to a magnet in your classroom. The iron filings will arrange themselves into the shape of the magnetic field lines. So it looks like Rob Black is still working on the telescopes there in Australia. We're going to go switch back to him now and let him show us a beautiful image of the sun in calcium K. That is quite fantastic, Rob Black. Good job. And remember, we're looking at exactly the same sun that we were looking at a second ago in the hydrogen alpha through Rob Black's Lunt Solar System's 100 millimeter hydrogen alpha scope. This picture shows us the sun in the wavelength of calcium K, which is 393 nanometers. This is a near ultraviolet image of the sun, meaning the wavelength is near the ultraviolet end of the spectrum. And he's also using the Lunt Solar System's 100 millimeter telescope to see this image. He has a special filter called a calcium K module that you can put into the back of any standard refractor, and you can see the sun in calcium K. And notice how he's got the same exact hot regions and sunspots that we just saw on the NASA SDO satellite. Now his image isn't quite as clear as it is from outer space, but it's pretty darn close. And you can have either of these telescopes in your classroom with a simple phone call or email to Lunt Solar Systems, because they have special products designed just for the classroom at all different levels of price. And if you want to have a permanent solar telescope in your classroom, then Lunt Solar Systems is the way to go, because they specialize in outreach and education. And they're also a great sponsor of our program. So this is showing you the sun in what's called calcium K. Rob Black has 3 telescopes on his mount there in Australia. One of them shows just a photosphere, white light. The other one shows this image, calcium K. And the other one shows the image we looked at before, the hydrogen alpha image. So look at how fantastically beautiful this is. And remember, this is not the internet. This is not some kind of fake sci-fi site. This is reality. This is what you can see through a telescope these days if you put a little time and effort into it. Very easy to do this hobby. You have to have a special telescope to look at the sun. You can't just use any telescope. But with a little bit of time, investment, and learning, you can show your classroom this, or you can have this in your own home and look at the sun anytime you'd like to. It's just a magnificent thing. And you know, it's floating out there in space. It's free for anybody who wants to look at it, and it's a floating chemistry and physics lab that you and your students can look at anytime you want to. As long as there's no clouds, you can see it clearly anytime you want to. I can't imagine a better way to get a young person into science than to go out and study the sun. It is unbelievable to watch what happens on the sun's surface. And again, the purpose of this entire program is to get you and your students interested in the sun and to study about our nearest star and learn more about it, because the future, you science teachers already know this, but your students may not, the future is in space. The future is not down here. Okay? The human race is at the point where it needs to begin traveling interplanetary and interstellar. This is the time for it to start happening, and your students are the ones that are going to make it happen. So if we ignore these students from 8 to 14 years old, we will watch them become incarcerated or get involved in radicalization or any other number of negative things possible. But if you give them just a little bit of your time and show some science to these students, they can change the world easily. And you students, anybody in this class listening to this broadcast, any one of you, even you can change the world with science. All you have to do is learn it. You have to learn some basic math and some basic science. Just go investigate the world around you. Take these cell phones and all this crazy stuff that we waste our time on all day long and just put them away. Go outside, tilt your head up, and open your eyes and look around at nature, because that is how you learn about the world. Any single person in your class, or your entire class maybe, could be the first people to land on Mars and walk across the surface of Mars. Any of you can do it, okay? There's nothing stopping you from going to the moon, Mars, or another star. But you have to start now by learning and concentrating on science, because that is the future. I promise you. Now, the way you contact our program is solarastronomy.org. You can go to the Facebook group for Charlie Bates Solar Astronomy Project. It has the addresses for all the different directors in all the different countries that we have. Excuse me. If you want to contact me personally, I'm happy to speak with you. We will help you teach your kids more about science, and we will help you get them involved in space exploration for the future of humanity. That's what we do. We never charge anything for anything we do. If you are approached by people that want to charge you fees for outreach, that's their business, but I would suggest that you go somewhere else where it's free, because this isn't about making money. This is about saving our future. So I want to thank you for listening in on our lecture today, and I hope that you've gotten something out of it and enjoyed it. Rob Black from Australia, thank you very much for providing us with free live images of the sun from the coast of Australia. Rob Black's about 20 miles from the Great Barrier Reef in Australia. Thank you so much, Rob.
Not a problem, mate. Not a problem at all.
And Pranvera Hysini, it's too early in the morning for her to speak with us because she's trying to stay quiet, but she's also totally dedicated to it in Kosovo. And if you're in Central or Eastern Europe, you can easily contact her. We've got people in Bosnia, Kosovo, Greece, Turkey, Israel, North Africa, all over Europe, UK, Germany, Brazil, South America, Costa Rica, Mexico, Australia, Philippines, China, Japan, India. We are spreading this as far as we can. because we believe it to be a great way to get your students interested in science. So thank you again, and this is Stephen Ramsden, the founder and director of the Charlie Bates Solar Astronomy Project, signing out from Atlanta, Georgia. Go study some science.